Hi everyone! In this video we'll learn how to interpret the results of a millimole reaction table for a strong base titrated with a strong acid. One of our learning goals is to be able to calculate the pH of the solution at any point along a titration as the strong acid titrant is added to the solution of base. There are 4 general steps we need to follow in order to ultimately calculate the pH. Calculate the millimoles of base and acid, and use that information to set up the millimole table. Interpret the E row of the millimole table to figure out where the reaction is on the titration curve, then calculate pH based on the results of step 3. The calculations and setup of the millimole table are covered elsewhere. In order to focus on the interpretation, we'll take a look at 3 completed millimole reaction tables, determine what the E row is telling us, and identify where this specific situation lies on the titration curve. Let's first take a quick look at a strong base titration curve to remind ourselves of what this looks like. A titration curve is a plot of pH versus volume of titrant. This curve begins at a high pH at 0 mL of titrant and decreases slowly for a while. When the titration nears the equivalence point, there's a steep, nearly vertical decrease by several pH units. Then the curve continues at a slow decrease until the end of the experiment. There are 2 points and 2 regions of interest on this titration curve. However, because there is no millimole table involved in the calculation of initial pH, we will not consider it any further here. So we have 3 possibilities. Before the equivalence point, which is the region between the initial pH and the equivalence point, the equivalence point, which corresponds to the specific volume of titrant giving reaction completion, and after the equivalence point, which is the region beyond the equivalence point, also called excess titrant. It is important for us to align the results of the millimole table to these 3 parts of the titration curve, before, at, and after the equivalence point. These millimole tables are handwritten, so you can see them in a similar format as you'll be writing them on paper. Here's a quick overview of the layout. The reaction at the top shows the net ionic equation for our strong base titration reaction. Our base, OH-, reacts with the titrant, H+, to form water. The water is generally not part of the calculation, so we draw a line through it to remind us to ignore. The rows correspond to the amounts of OH- or H+ involved in the reaction. I equals initial, which is what we're starting with in this particular situation. C equals change, where we subtract the lower initial amount from each reactant. And E equals end, which is what is left in solution after the base and the acid have reacted. In this first example, we see that all of the OH- in solution reacted stoichiometrically with the H+ that was added. There's no excess of either reactant. And this is the definition of the equivalence point. When both OH- and H+ are at 0, the reaction is complete and we are at the equivalence point. In our next example, we see that the H+ goes to 0, which means that the amount that was added was used up. When the titrant is at 0 and the reactant is greater than 0, we are before the equivalence point. There's still some hydroxide remaining even after this reaction. This tells us that the reaction is not complete because some of the hydroxide didn't react. This titration is somewhere in region 2. And our last example shows that the original base is fully reacted because it goes to 0. However, there is excess hydrogen ion remaining. Here, we are after the equivalence point. There is no OH- left to react with the H+, so the H+ begins to accumulate. This situation puts us in region 4. To recap what we learned here, we can interpret the E row of the millimole table to align with different parts of the titration curve. If the hydroxide is greater than 0 and the hydrogen ion is at 0, we're before the equivalence point. If both hydroxide and hydrogen ion are at 0, we are at the equivalence point, and if hydroxide is at 0, but hydrogen ion is greater than 0, we're after the equivalence point.